So the next speaker is Stefanie Rynders from the University of Southampton, and the topic of the talk is modelling dynamics of the Marginal Ice Zone, including combined collisional and EVP rheology.
Good morning, everyone. We're staying, well, actually at the National Oceanography Centre in Southampton. Started a postdoc there, but yeah. So, better now. So, first, I want to thank the organizers for letting me speak today. So, what I'll be talking today about is sea ice rheology, and try to come up with a rheology that's appropriate for the Marginal Ice Zone. Now, let's go through some motivation first. We've been doing or working on several topics at NOC that are connected to the Marginal Ice Zone, and the reason why we are putting attention to that is that the MIZ is becoming an ever more larger part of the sea ice cover in the Arctic, and more important one to represent well. But well, at the moment in sea ice models, a lot of MIZ-specific physics is not there, and so we want to update the models and see if we can improve simulations if we account for that. So, well, one thing is to try to improve projections or make sure sea ice models stay up to date, but also other thing, and that was a project my PhD was connected to, is operational forecasting, because Marginal Ice Zone, that is where ships might go, so that's where people are interested in. So, Marginal Ice Zone, officially it's defined as the region of the ice cover that is affected by waves. Now, for the rest of this talk, we'll stick to ice concentration limits. So, the MIZ is between 15% sea ice concentration and 80% sea ice concentrations. So, on the figure on the slide in the inset shows satellite observations of the Marginal Ice Zone width for the Arctic going back about 30 years. It shows the MIZ width in summer in red and in winter in blue. And you can see that in summer, actually, the MIZ has already increased quite a bit. So it's an increase of 30% in width over 30 years. That's quite large. And also for the projections of the models at the moment, that's what's shown in the large plot. And it's projected at the relative area of the MIZ in the Arctic compared to the total ice covered area in the Arctic. By the mid-century will be about half of the sea ice cover. So then for sure it will become more and more important that the sea ice models can model MIZ accurately. But MIZ is not only something for the future. If you look at in the model now and you calculate the relative area of the Marginal Ice Zone compared to the total ice covered area, actually in part of the year, the MIZ is already quite big. So if you look in the Arctic in summer, there's some interannual variability in the model, but in some years it's already hitting the 50% relative area, so that's quite big. And also, well, in the Antarctic, it's even more important, right? So, coming back to the rheology then, pack ice and MIZ ice behaves a bit differently in terms of internal stress and motion. So, in the pack ice, in a way you can say that internal stress comes from mean state of the sea ice, also mean motion of the sea ice on things on large scale. But in the MIZ, you can have extra internal stress because of the turbulent motion of sea ice floe that you can have. It's a bit like molecules in a gas, right? That's the analogy that we make. So the pressure in a gas, it's caused by turbulent motion of the molecules that are moving around, bumping into each other. So for the MIZ rheology, the important thing also will be the turbulent kinetic energy of the sea ice floes this time, so how much they're moving around. And from the analogy with the gas, we also call it granular temperature. So it's not temperature in Kelvin, it's kinetic energy meter square per second square. And I'll use both terms in the rest of the talk. Now, people have done some work about this on this topic before. So there is a rheology that's specifically made for the MIZ. It's called collisional rheology. So that's been done by Haley Shen already back in the 80s, but she actually never put it into the large-scale sea ice model. And then we still need something for the back ice, right? Because we want to create a model that is suitable in both regimes in a way that you don't have to choose between two rheologies, that there are no abrupt changes between the two. So for the back ice, we just use EVP rheology. I've been using the size sea ice model, so that's a standard choice. And what we'll do, but we'll see it in further on, is that we add the effect of, or the internal stress that's caused by both mechanisms. And the granular temperature we'll see will cause a smooth transition between the two. So, combined, why is this going back? Anyway, so this combined rheology, it's something actually Danny came up with 10 years ago or so. And what you do is, because of the way you can write collisional rheology, the EVP rheology in the same, according to the same formalism, like it's using shear viscosity, bulk viscosity, and replacement pressure. It's very similar makeup. It's quite easy in a way to add up the two. So these are the equations for both terms. So in the end, we'll just add up the two terms. What is something to notice about collisional rheology? Maybe there's granular temperature in there, GT, that feature, so we'll have to calculate that one. There's also flow size, so that's maybe something of a new variable in the model. So for parts of the talk, we'll use just standard 300 meters, but some of the simulations have been made with variable flow sizes. So now the equation for the granular temperature itself, not going into the details, just sketch the layout. So in the end, we're just looking at the turbulent kinetic energy. So what we'll do is to list different sources and sinks of energy, and then calculate the granular temperature out of it. So the main source of energy are turbulent fluctuations in the ocean currents and the wind that exerts a drag on the sea ice floes. And a second source of energy is wave surge. Now, there's internal stress can be both a source of sinks of energy, it's redistributing energy, and then big energy sinks are rubbing between flows and collisions between flows because they're not perfectly elastic. So that is the general equation. Now, if you look at only the most important terms in this equation, the turbulent energy source and the rubbing and the collisions between flows, which are the main sinks of energy, you can actually solve this equation analytically. And so the figure on the slide shows the replacement pressure you get from that plotted in terms of sea ice concentration. And you can see that for the lower ice concentration, well, going up to 75, 80% sea ice concentration, which is the marginal ice zone, what collisional rheology is adding, which is the blue curve, is actually, in terms of pressure, a lot higher than what EDP had there before. So some of them too becomes the red curve. So this increasing pressure in MIZ is something we'll see happening in the model later. In terms of viscosities, the collisional part of rheology is adding some viscosity, but actually it's very small compared to DVP viscosity. So it's not something that will have an effect really in the model. Now, model configurations. Actually, I've been using two different configurations. One is a more realistic global model, and the second one we'll see is an idealized channel model. So for both, actually, I'll be using the NEMO ocean model coupled to the sea ice model. The global configuration is a 1 degree resolution, so it's 35 kilometers in the Arctic about, because there's some the grid is getting finer a bit, but it's still a bit low resolution to actually look at MIZ specific, so we'll just look at larger scale things. The forcing set I'm using is, we don't have an atmosphere model coupled to it, just ocean and sea ice is a tracker forcing set, and I'll just have 10-year long runs. And for them, flow size, evolving flow size we'll be using for some of the runs. We need wave information to make flows break up. So the wave information we use comes from ECMWF, and yeah, there's some kinds of fancy stuff going on to equalize the wave fields in the sea ice cover, which is what Lucia put in the model. So you'll have to ask her about. But for now it's not really important. Idealized model configuration then. So what we'll use is a channel model that is made to represent the Southern Ocean. So the conditions we'll use are Ross Sea conditions approximately, but it's not that important in a way. You can make it represent other parts of the globe, is greenly current or something. So the channel is an east-west boundary condition, and it is 2,000 kilometers in the north-south direction. Actually, it's made, or the settings we chose in a way that in the zonal nothing really happens. We'll just look at the north-south cross sections of the channel. There's two different setups, being more or less coupled for the sea ice and the ocean. So we'll use a completely uncoupled one and a completely coupled model. The idea of this uncoupling is to try to separate effects that are intrinsic to the sea ice from mechanisms that involve the ocean. Now, first thing to look at is the granular temperature we get in this channel model. So the plot on the left shows in blue sea ice concentration and green granular temperature. So comparing the two, you can see that in the parts of the sea ice cover where the concentration is quite low, in this case below 75% or just regular MIZ area, we see that that is where the granular temperature actually has substantial values. In this case there's two peaks, but that doesn't actually matter. Normally it doesn't happen. Now, this granular temperatures that we've calculated it's the result of different energy sources and sinks, so we can also see which one are important in which conditions. So again, taking the cross-section through the channel, on the figure on the right, I've plotted all the different terms of the equation, and what shows up is turbulence is the most important energy source that we expected. The waves in the pink show up at close to the sea ice edge, and then in terms of energy sinks, collisions are the most important energy sink at a relatively low sea ice concentration, and if we move into higher sea ice concentration, it's the rubbing between the floes that take over, and in all of them together set a balance of the granular temperature. Now, what actually then happens in the model? The thing we'll be looking at is sea ice concentration again. So this figure shows the sea ice concentrations from both the uncoupled simulation and the coupled simulation, and just looking at the one on the left, showing ice concentration between the standard EVP rheology and the new combined rheology, which is the one in blue. There's actually quite a striking difference between the two. With the new rheology, we have a much wider MIZ. But then if you compare it to the figure on the right, actually suddenly there's no effect on the sea ice concentration at all anymore. This is when you fully couple the sea ice cover in the ocean. So what is happening when you couple completely that overrides this effect? Now, to find out why, it's instructive to look at the different terms in the momentum balance of the sea ice. So I've plotted different terms, just also cross-section through the channel for the different situations. And what shows up in both of them, the effect of the tilt and the Coriolis force are quite important for the momentum balance. They're very big terms. But then what the third important term is quite different between the two situations. In the internal, in the uncoupled channel, it shows that the force due to internal stress is actually quite important for the momentum balance of as a third term. And in the coupled model, it's completely different. Internal stress suddenly disappears. It's tiny, doesn't matter at all really. And suddenly we have oceanic drag that is very important. So what happens in the uncoupled simulation? We have quite very slow moving ice, also quite thick ice. In the coupled simulation, the ice moves much faster because now it's suddenly feeling the push from the ocean currents. It's also much thinner because ice gets exported northwards and it melts. So what then happens? Well, in the uncoupled channel model, internal stress, as you see, is important. So there, if you do something to the internal stress, like increasing internal stress in the MIZ due to this collisional contribution, you actually can see the effect on the on the sea ice concentration on large scale. In the coupled channel model, actually internal stress doesn't matter at all. So whatever you do to it, you still don't have an effect on the ice cover really. So it's something to think about when you look at the global model, what we'll be doing now. So first look at granular temperature. These are just some plots from the model. The lines in pink are ice concentration bound, so 15% and 80%. So what is in between is the MIZ, and again it shows, like in the channel model, the MIZ is the region where you have the high granular temperature. It actually fits quite neat. could be, in principle, a way to define an MIZ from dynamics rather than concentration. Now, in the global model, we can try to validate this granular temperature a bit. So there's two options we'll go through. First one is to use accelerometer data. So the data I've used comes from the CV experiment. And well, the raw data you get out of it is what is shown in green, so acceleration measurements. Now, if you integrate acceleration, you get sea ice velocity. So if you then remove the mean sea ice velocity, what is left can be called the turbulent velocity of this particular sea ice floe. That is what's shown the pink on the figure on the bottom. You can see that it's very spiky, it's very variable on the very small time scale. So actually the whole measurements of this one is just, about a day. So it's very, so it changes very rapidly. Now the average fluctuation velocity squared to get out of it, or the what we call granular temperature, here is something like 5⁻⁴ meters squared per second square. Now we can also calculate this value or average this value for the region in the model that corresponds to this region in the Pulver Sea where the experiments are made from, the same kind of ice conditions, and actually we get a number that's quite, that's not too far off at all, really. We're not aiming for exact correspondence here, but just to get the order of magnitude right is already a big thing if you see how variable the measurements can be. So I think I'm going to be quite happy with that one. Now, another possibility in principle is to use buoy tracks to calculate the turbulent kinetic energy. Well, first the fluctuation velocity, because the granular temperature is actually the variance of the trajectory of a sea ice floe. Now, Pierre and Paul has been looking at this, at the trajectories from buoys. I've reported the variance. I've calculated granular temperature from those. That's what's in the table. And what we see here is that these values are actually an order of magnitude larger than the ones in the model. Now, I think the most probable explanation for this is the observation frequency. So their frequency of measurement is 12 hours. So you're using the inertial oscillations tide signal, so that will definitely increase the velocity fluctuations you have. Now, in the model we don't actually even have tides, and also the velocity fluctuations we're thinking about in the model are actually on a much larger time scale. So even though these observations don't really match to the model, don't seem very good to use, I think it's still in principle a valid method. The only thing is that we need the buoy positions at a much higher time frequency than 12 hours. Now, what is actually the effect of this combined rheology in the global model this time? So, actually, not much happens at all, really. We have some effects, but they are very small. One thing that we see, which is quite curious, is that combined rheology is causing a spin-off of the Beaufort gyre in the sea ice model. And the way that happens is actually in summer, sea ice concentrations go down a bit, so you come into situations that are like the marginal ice zone, so a bit above 80%, and there you still have an extra internal stress because of the collisions between the floes. That's what we saw in the beginning. So this slide actually, impact of the collision rheology only goes down to 0 when you're already really within the pack ice. Gone too far. So what then happens because if this internal stress increases in a lower concentration area? What happens in the model is that there is a redistribution going on of the sea ice thickness. So their ice has been converged into the Beaufort gyre, and then the outside of the gyre as a lower sea ice thickness now. And then what happens in the end is just this thinner ice is just moving faster. So this figure with the change in mean ice thickness is pretty much the same as the velocity change. Now, can think back a bit about the channel model and see what we saw there is what we can pull it through to the global model. So actually, what we saw there, or what we can conclude, is the effect of the collisional part of the rheology we can expect to see in a situation where the ice is not moving super fast, so the ocean drag is not too large. Also, you need a quite thick sea ice cover to have a substantial internal stress there. So, Beaufort gyre, even though it's moving quite fast already, can be a good situation where you can see the effects of things actually more than in situations like East Greenland current, where the sea ice is moving very fast and ice is already quite thin. So there we'll have the ocean drag being very important, probably, rather than internal stress, and whatever you do with them. And I said rheology won't matter much there. Some applications of calculating granular temperature. I've been working a bit for the project called SOS earlier this year. The full title is Safer Operations at Sea Supported by Operational Simulations. It's quite long. So what we've been doing is to estimate loads, calculate loads on offshore structures using the environmental information from the model. So we'll account for loads from ocean currents, from waves, also for sea ice, what is interesting here, and you can do wind as well. The standard way to calculate load on offshore structure from currents and waves is an equation that's called the Morrison equation. Now, we've added sea ice loads to that in a way that's very similar to the distinction that's made between the current and waves. So, static sea ice load, mean state, and dynamic sea ice load, or turbulent kinetic energy, that's been added. We've calculated, and what comes out of it is something like here, which is not terribly clear on the projector, but anyway, the figures show the relative contribution of the sea ice load, or the dynamic sea ice load, to the total load on the structure. So the figure on the right, on the left, shows a total sea ice load, and there you can see sea ice becomes important in several places around the coast of Canada, also in the Hudson Bay. Sea ice can be an important part of the loads on structure. If you only look at dynamic sea ice loads, so that is really the collisions with sea ice floes. So for that we use this turbulent kinetic energy of the floes and also flow size. And what comes out of it is actually dynamic sea ice load can be a very important part of the total load, even even to the extent that the contribution of the wind and the ocean and currents is almost negligible. But that just happens in very specific concentrations, again, around the coast where concentration of sea ice are probably a bit lower but actually close to the coast and is also a place where people build offshore structures. So it's quite can be important thing to take into consideration when building structures. So outlook, what I maybe will be doing in the future is maybe looking at Antarctica a bit more. So in the ACC area probably won't see much effect of granular rheology, but further or closer to the coast where the sea ice velocities are not very high, you might actually get some influence of the collisional behaviour. Another thing to do is update wave search equation and try use that in the global model. See, don't think Luke is here, but yeah, missed this talk unfortunately, but yeah, that would be nice to include that and maybe have some better results in the global model. A third thing is thinking about mixing a bit. So at NLC we actually been doing some more work on mixing recently, and the turbulent motion of the sea ice floe bumping right is one thing that can cause mixing, which is not accounted for in the models at all. Whether it's an important contribution, I don't know, that's a different matter. We'll have to see that, but it's something we might try to look at in the future. That's everything I want to say about rheology really, but I have a little bit of time left, and I have a topic I wanted to show or ask your opinion about. So, and that is ice edge jets. Now, in the channel model, in certain situations, which is when you use variable flow size, which we have, and independent of rheology, what we see happening is that we get an increase of ice and ocean speed at the sea ice edge, or very close to the sea ice edge. Now, in terms of magnitude, it's not very large, but ice edges people are talking about in literature are much, or from observation, are much larger than what we see in the model. But it's quite curious. It only turns up in certain situations, and it's nothing to do with rheology in principle. The ice concentration also behaves a little bit curious, and we can probably explain that a bit later. Now, this slide shows the different components of the velocity of the ocean and sea ice. So, ocean is in red and sea ice is in green. And actually, what we see here, this intensification of currents in the along ice direction, the zone is actually not large at all, but in the meridional direction is quite striking. Actually, the definitely ocean velocity, or is not quite doubling, but almost. So it's very big effect. Also in the sea, I've seen the same thing. And so this meridional velocity is the northward drift of the sea ice. So how it can happen that suddenly the ocean moves a lot faster northwards and then goes down again is that we have an overturning cell under the sea ice edge in the ocean currents. So this plot shows vertical velocities. Red is going upwards, blue is going downwards, and what it shows is around the 1,000 kilometer mark there is actually quite clear overturning edge under the sea ice, and this is what shows up in the velocities, but also in the sea ice concentration. This plateauing of the sea ice concentration in the MIZ is actually right on top of this overturning cell. So why this thing actually happens? Well, I don't know really. Well, what we've done in the end is we've changed the flow size, right? Now we're using variant flow size instead of 300 meter flows. So what we've done effectively is increasing lateral melting gradient. So it's also increasing the concentration gradient, EC2, and then also the roughness of the surface that is seen by the atmosphere or by the ocean will be different, just in terms of sea ice concentration. I'm not actually using form drag, so it doesn't directly see the effect of the floe size. But then it's not really clear what happens. Well, in principle, there are two big possibilities. Either is the reference gradient that causes this overturning cell to occur, so maybe increasing some kind of threshold in roughness, or alternatively it's buoyancy driven. Because of the lateral melting, you'll have extra fresh water there and change the buoyancy structure. Now, what other people have been proposing about the mechanism how sea ice jets, which are observed in real life, occur. So Harry Horton has one possibility or idea, which is that because of the change in roughness of the surface, if you go into more into the black ice with higher ice concentration, it can create a jet in the atmosphere and also the ocean. Well, we don't have in this model an actual atmosphere model, so there's no real interaction going on. Well, to some extent, but not really in a realistic way. He proposes that you should have these atmospheric jets in the atmosphere, which is something you have to impose in the forcing field if you don't actually have an atmosphere model. That's not something we have done here. I haven't imposed any sort of jets at all, but still it is happening. In the paper it also, well, firstly, jets are much stronger, but also they happen on a much larger scale than in this model, so maybe it's not quite the same mechanism. Alternative, the combined rheology also can cause sea ice or ice edge jets. That is something that was in the paper of Danny. If you do some analytical solutions of the equations, but actually here we don't see any effect of the rheology at all. It's not that the jets are appearing when you change the combined rheology, which is actually what would have expected at first. Also there's a problem about resolution. This rheology driven jets actually happen on a much smaller scale this time than what we have in the model. So this model output I showed is from a model that has a resolution of 12.5 kilometers. And for the rheology, these jets, you're looking at some scale of maybe 5 kilometers or something. So we're not resolving at all what could be happening there. So maybe actually if I have a higher resolution, we'll see this effect of rheology, but in any case, it can't explain what is happening here either. So third option is still density driven currents that occur and can trigger this overturning cell behavior. But that's what I wanted to get from you. Maybe people have ideas about other mechanisms that could trigger ice edge jets to occur, even if they're not very small, not very large in this case. Would be interesting to see if there are other possible explanations that we might look at. So that was it for me. So thank you for your attention.
So we had 5 minutes, and there's 2 parts to the talk. And Stefanie's invited us to have a wee discussion about features along the edge, along the marginal ice zone edge, in particular jets. I'm reminded of the late 80s and 90s where everybody got terribly enthusiastic about jets, eddies, upwelling, downwelling, you know, you name it, and there were all sorts of mechanisms that people were devising little models to explain. I was part of that as well, but I don't think I came up with the answer. So anyway, it's open for discussion.
Yep.
Yeah, Dan.
Okay. So in the second part, we invited the discussion on jets. So obviously, I'm the author of that paper about carbon et al. Hey, that's just it wasn't et al. It was just me.
Yeah, could be.
I just noticed that.
Standard mistake.
Yeah, that's not that. It definitely is not the mechanism. Okay.
No,
There's no way that's the mechanism. Okay. That's a very narrow jet of the width of maybe 5, maybe 10 grain widths.
Yeah.
Okay.
So
So that is tiny, and your simulation's already shown that it's got nothing to do with that. So you can throw that out straight away. Okay.
Yeah.
Right, well, we've narrowed the field down.
The other paper, I am the second author on. Okay. So you don't have form drag in your model, right? But you do still have increased roughness when the ocean goes underneath the sea ice.
Yeah, just because of the ice concentration. Yeah.
Yeah. So Harry's paper shows that you would expect. Well, actually, no. Let's be more precise. Julian Hunt's paper shows that a flow over increased roughness will create an edge jet of the width of the velocity radius. Okay. And then that is felt by the ice cover in the form of this enhanced flow, the ice jet. So that could be the mechanism, because you do have an increased roughness as the ocean flows beneath the ice.
Yes.
So what's the velocity radius? And you can test your model in various ways, like you could, for example, make the drag coefficient of ice the same as the ocean, and you immediately determine whether that's the solution. Regarding the buoyancy, you can do a similar thing to switch buoyancy off.
Thank you. Other, Hayley?
Can you explain again, how do you account for the wave surge in the granular temperature balance?
So what I've done, Luke, who isn't here, or is here, I haven't seen you yet. You're too. No. Sure. So, well, you've been at a paper on the motion of a sea ice flow in a wave field, and you can. Well, there are several possible models to try and calculate the displacement you get from putting this flow in the wave field, and then just having a formula way to calculate displacement. What I did is just say, well, actually you have to reach the full displacement of the sea ice flow if you assume it just happens on a monochromatic way, just moving up and down the troughs of the waves. Is that well, amplitude has to be gained over the period of the wave, and you just divide the stuff and get some kind of velocity of the flow out of it, and so the square of the velocity is kinetic energy. So that's what I took and what I put in the channel model. But yeah, Luke has now got better formally to calculate this amplitude, so I think I'll have to update the calculation here to get more realistic situation.
Got another question.
You mentioned extension of the Morrison equation for the balloons of sea ice. Maybe you can just elaborate. Is it changing the CD and the CN coefficient, so you add some other terms taking it into account of density currents effect? I mean, what is the modification of the Morrison equation?
Well, the CD and CM coefficients, they just stay there as parameters in the equation, right? You just have to change the internal friction coefficient to have to represent sea ice friction rather than ocean current. But apart from that, it's what the Morrison equation uses is the velocities of the ocean, just velocity of the mean current and also velocity that's induced by the waves, to calculate the stress on the total structure of the volume of the water that you have pushing against it, right? So what we did, instead of having a volume of water pushing against in this case it's just kind of monopile structure, we have a volume of sea ice that is pushing against the structure. So
let's modify the coefficients. It's the same form, just with empirically new coefficients.
yes, it's very similar. There are a few things we have to add, like sea ice thickness is something we have to take into account, and also for the dynamic part, so the equivalent of the wave motion, we now have something that's actually more of an kinetic energy calculation of a sea ice flow that bumps into something and comes to complete rest. So there you have to add the flow size, which is something you didn't have before in this equation. There you only had a velocity of the wave-induced field.
Okay, I think we'd better stop there. You can ask more questions over lunch. It is lunchtime. Please be back by 1:30. I'd like to thank all the speakers again. We started with a bang this morning with 3 excellent talks, and let's hope that the workshop continues in that vein. So I'm stepping down now. I'm no longer